Hello. In the last video, we have seen how we can use the wave equation to generate waves in Unity. Now, that system was using CPU to generate such waves. Today, we will be transferring this process to GPU to allow us to scale it up to much larger textures. Now, here we have our scene, and we're going to start with creating a compute shader. And let's name it wave compute. We are going to create a C# script that's going to manage our waves. Let's call it Wave Manager. And finally, let's create a plane that's going to make the water surface. Let's assign it to the plane. We're going to start with assigning our compute shader to this wave manager script. Let's call it wave compute. And we're going to have this compute shader work, or run our waves equation. And it's going to be calling it from this wave manager. And we're going to need these textures that's going to keep the information regarding the different states of the wave. So we're going to have n state, n-1 state, and n+1 state. We're going to have a resolution vector, and now we need to initiate our textures, and these textures have a size. These textures have to have a size assigned by the revolution. So we're going to create a function that's going to initialize these render textures. So we use the reference keyword there. And the depth is going to be 1. So just there one layer. And the key thing is here, it is important to remember that if you have watched the previous video, each cell can have a negative or a positive value. And when the water is stagnant, the value is 0. So we need a texture that can store negative values. Now, usually textures store vectors that is ranging between 0 and 1, each indicating the amount of color. So we can't use them. Alternatively, we have other texture formats that we can use. So we need a texture format that can carry negative values as well as positive ones. In other words, we need it to be able to have signed values. So we're looking for something. Normally, normal texture has the U norm. We're going to use the S norm. S norm indicates it's a signed value, which means that it can take a negative value. We can again use RGB. That's fine. We don't really need all 4 channels. RGBA, we don't really need all those 4 channels, but rather have extra channels than not enough channels later. We make sure that we enable a random write, and then we create the texture. And all we need to do is initialize texture for all three states. So every update, we're going to be calling this wave compute. And in every update, we are going to resend these textures to the compute shader for processing. We're going to start with setting the textures inside the compute shader. So we're going to first start with identifying the kernel index, which is 0, and then the name of the variable that we use in the shader. We can use the same name and state, and finally the texture itself. Also, we want to send the resolution information. We can send as an array of ints. Finally, we will send the resolution information to the wave compute. To do that, there are two ways. We can send as a vector, or we can send as an array of ints. In this example, I will use an array of ints. And to do that, we are going to create new int array using the resolution vector. Next thing we have to do is dispatch. It will start the process. First, we start with defining the kernel number, and then we have to identify thread group size. At the moment, inside our wave compute script, the number of threads are defined by 8 by 8 by 1. So we have to divide our resolution to 8 to be able to get thread group size. Next thing we're going to do is working on the wave compute shader. Now it has two parts where we're going to be entering our variables here. And then in the CS main, we're going to enter our code. Now we need three textures. These are going to contain the current, previous, and the next states of our wave field. We don't need this anymore. Now inside the GPU, the CS main function will be called for each pixel of our textures. So we are going to get the value of each pixel that is called is associated with and process on that. The ID parameter corresponds to the individual pixel that core is associated with. At first, I'm going to store these pixel information, in particular the first axis, so which corresponds to the red channel. We're going to store this in individual variables so we can access them easily. The information we need is the current state of the current pixel and the previous step state, so n-1 state, and we need the information from neighboring pixels. Getting the coordinates of the neighboring pixels is easy. all we need to do is adding or subtracting an unit vector from the ID xy, and we'll get the coordinates of the neighboring pixels, and then we can just get the values of these pixels using that new coordinates. So we're going to calculate the value n in n+1 state. Now we're going to store it in a different variable first. Let's call it new wave height. And that's going to take 2 times the current position, the current pixel value, minus previous pixel value, plus in the previous video we had CFR squared, which corresponds to 0.25. So I'm just going to keep 0.25. .25 seems to be working well, so I'm going to stick with it. And then we're going to add all the neighboring values and subtract 4 times the current value. This is where the values in the neighboring pixels is going to affect our wave height. And now we can transfer this new wave height to the current pixel position in the next state, n+1 state, and an ID xy will be equal to new wave height. So we're going to create a new color, which is represented as float 4. Red, green, and blue is going to have the new wave height, and 1 for indicating the alpha channel. Let's add our resolution as well. Okay, it seems to failed because we don't have a resolution value, which was 0, now it's 100. And we also need to assign the wave compute, and the render textures need to be empty. We still have an issue. I believe the problem was we used uint instead of uint2. Uint2 is a vector, uint will only give us a scalar. Okay, so finally we don't have any errors. Now I will create a vector to identify the center of a ripple effect, so we can see that our wave field is working. Well, we're going to have the x and y coordinates indicating the position on the texture, and z is going to contain the amount of wave height that we want to set at that particular coordinate. We're gonna set it with a set vector function and send the information to the compute shader. We can also set the resolution here. Now the problem is that the resolution itself is a vector to int, and we can't send an integer to the compute shader. There has to be a float. So every update we're going to convert the resolution into a vector that contains floats and send to the compute shader like that. Well, no errors so far. That's good news. If this particular call corresponds to the coordinates of the effect, then we want to change the wave height by the z-axis of our effect vector. Currently, we can see in the middle of the texture, our vector is changing the wave height. However, the simulation is not working so far because we need to pass the n plus state to end state and end state to n minus 1 state for the simulation to work. We're going to be doing that using graphics copy texture, which is a straightforward way to copy one texture to another. We have to make sure that we first pass the end state information to n minus state and then n plus 1 state to end state. So we can see the textures are updating with the ripple. However, we can't see that on the scene at the moment because we need to transfer that into a material as the main texture, and then the material that is attached to the plane can show us on the scene. Just like in the previous video, we are going to create a reference to our material inside the Wave Manager script, and then we're going to assign the main texture with the end state. Now I can change the center of the effect, and it should also move together. Remember, this texture has negative values. However, we can't seem to be able to see these negative values on the texture naturally because there is no negative red. But instead, what we can do is we can add an emission, and that emission will be counteracted by any negative value. Alternative to this is to create our own shader. Another issue, you can see that the edge, there seems to be a border that doesn't have any waves. That is because our resolution is not completely divisible by 8. So if we change it to something like 256, which is divisible by 8, we are not going to be seeing those. The ID x and y always returns a whole number, but our effect is not. So we have to make sure that our effect is converted to the nearest integer so that there's a seamless transition for the center of the wave. Now it's time to include the dispersion. Just like previous video, dispersion is going to control the how much the waves are disappearing with every cycle. So all we need to do is set the float to dispersion from the wave manager, and then in the compute shader, the dispersion is going to be multiplied with the new wave height and assigned back to it. Last time 0.98 seemed to be very good for this value. The next thing we are going to do is we are going to have a texture that's going to render our obstacles on the wave field. We have to make sure that the obstacles render texture has the same resolution with the resolution of our wave field. By doing so, we can actually have these obstacles reflecting the waves back. To be able to do that, what we need a render texture, obstacles render texture, which is going to be rendered by an additional camera. All right, this camera first have to look downwards towards our waves. It has to be centered so it can view everything in on the view. It has to have an orthographic projection. Now the projection size is too large, so we need to make it smaller so that it can only render our plane. We can simply set the obstacles as our target texture. So it's going to have a size defined by this texture. Also, we don't want it to render everything. We only want it to render certain layers. Here I added block and sink, which are the two layers that I'm going to use for either blocking the wave or creating a ripple effect. So it's time to create some blocks. Now the blocks themselves doesn't necessarily have to be on the block layer. What we can do, we can create additional sprites that are going to be unlit. And these unlit sprites won't be affected by the environmental light. And we can set the layer of these sprites as the block, and so that these sprites will be rendered, but nothing else. All we have to make sure is that these sprites are going to look towards the camera, and they're going to be silhouette of these blocks that we want to use. And if we are going to make some rocks, for example, then we have to make sure that they have the silhouette of the rock. In our case, since we are using cubes, we can just use square sprite so that their silhouette can be seen by the camera. As you can see, the obstacle camera is rendering only the red of our sprites. Now I set sprites to red because we are going to use the red as the color indicating that it is going to be blocking. and we can use another channel, for example green, to indicate that it is going to be the ripple. So we're going to send these obstacles text to the compute shader, so the compute shader can check whether or not there is a block in that particular position. Now at this position I can check for the value in the same position in the obstacle text, and if the red channel is 1, that means for complete red, then I can block. Blocking is simple. If you remember from the previous video, all we need to do is to set this value, set the new wave height to 0. Don't forget to assign the obstacles text to our wave manager. It's always beneficial to make sure that the size of the obstacle text is equal to the size of our resolution. So I'm going to leave an assertion here. It's going to run only at the start, so it's not going to have any performance impact anyway. I'm going to make sure that they are of same size. What we are seeing here is that the texture is, I think, looking upside down. So we can simply rotate the camera 180 degrees so we can get the right texture. Now you can see, especially at the corners, the blocks are reflecting the waves back. Now it's time to create a boat, well, a representation of our boat in this case. Now this capsule is going to be our boat. It's going to sink the water, and we're going to create a capsule sprite, make it look upwards. Set the layer to sync. And we're gonna set the color to green, which is the second channel. And we have to make sure that sync layer is also included in the culling mask of our obstacles camera. Once we do that, we should be seeing in the render texture the green color, which is going to indicate where the water is going to have, it's not going to be 0, but it's going to be below the surface, so it's going to have a negative value. Now I'm going to add player script, a player controller script that I have prepared before. It's rather simple. It just translates the transform depending on the input. It's a very simple script. And now we're going to use them. We'll be able to use the keystrokes to move our boat. However, at the moment there's no wave or there's no ripple effect. That's simply because we haven't told the script yet about the green channel. Now, since I'm comfortable with the turn speed and the speed of the boat, now we can go to the compute shader, and we're going to say if the obstacle text is returning in the green channel is returning 1, then we want the new wave height to be negative. As you can see, it's creating ripples, and these ripples are being bounced back by the blocks. It's pretty nice. It's a very nice effect. We can change the size of the capsule sprite if you want to get rid of all the black areas around our boat. Now, all we have left is to show how we can actually increase the size of our water surface. Well, you just multiply the texture size by 10 in both directions, so it's like 100 times larger. We have to increase the size of our plane by scaling up 10 times in X and Z directions as well. And we also have to increase the size of the camera from 5 to 50. So multiplying everything by 10. This way we have a larger texture. Now this is not going to be a problem because GPU can handle this. Once we choose a nice color for our surface, it will be nice if we have transparent as well. Yeah, maybe let's move. This looks more like water surface. Make sure that you increase the resolution by 10 times as well. Now we can play. I hope you found this interesting. In the next video, I will try to show how we can use the displacement shaders so that we can simulate wave formation in 3D. Thank you for listening, good luck with your projects, and see you in the next video.